To start off, I want to remind you where we left off last time. So in our last Vodcast, we started out by talking about the de Broglie equation, which is an equation that basically relates mass to wavelength. So anything that has a mass has a wavelength. We also talked about the uncertainty principle, quantum mechanics. We went through the different quantum numbers, and then we ended by talking about the different orbital types and their shapes. And what we're going to go in today is how to do electron configurations and also looking at orbital diagrams as well. So a little bit more vocabulary that we didn't really get into in regular chem. So you should remember the orbital diagram. That's what we're looking at over here on the right hand side. Remember that each of these boxes you would put some arrows in here. And so if we were looking at an orbital diagram, or basically a hydrogen atom which has one electron in it, orbitals that would appear in the same energy level, they have a special name. They're called degenerate. So orbitals that exist in the same energy level are called degenerate. So for hydrogen, it's going to have a bunch of degenerate orbitals. So for example, in the 2s, we would also, the 2p would basically be at the same spot in terms of energy. The 3s, 3p, and 3d would basically be in the same energy level. Those would be called degenerate orbitals. Now what happens is when you have multiple electrons in your atoms, you get repulsion between the electrons, which drives the orbitals a little bit apart. And so they don't actually have exactly the same energy anymore. So not all of the orbitals, not all orbitals on the same energy level are degenerate. And you also see that you start to have some overlap in the between the different orbitals. So for example, the 4s ends up being lower than the 3d. So the third and fourth energy level are actually overlapping. And that again I'll remind you, has to do with a little bit like the shape of the orbitals themselves. So we call this the Pauli exclusion principle. We did talk about this in regular chem, but maybe not exactly in these terms because we weren't talking about quantum numbers. So no two electrons in the same atom can have exactly the same energy. That means they don't have the same set of quantum numbers. And in your notes, there may be a typo here. So if you look where you're filling in Pauli exclusion principle, if you look to the bullet point underneath that, it says, therefore, two electrons in the same energy, in the same atom can have identical set of quantum numbers. It should say no two. Again, this is very important. No two electrons have the same set of quantum numbers. So that means they must differ by at least one of their quantum numbers. And this is important for when we do electron configurations, and also when we go in and if we wanted to fill in an orbital diagram. So I want to remind you a little bit about electron configurations here. So if you look off to the left, we have some one energy level. We're looking at 4. We're looking at the p orbital and the 5 electrons here. So we write electron configurations in order to denote where electrons are in the atom. And the most stable organization is usually what we're writing an electron configuration for, although we can write an electron configuration that represents an atom with excited electrons. But this lowest possible energy configuration is called the ground state. And each component of the electron configuration is going to consist of, we have first this number right here, which is in dark blue. That's going to denote or like tell us the energy level that the electron is in. Then we're going to have a lowercase letter, which is either S, P, D, or F. That's telling us our orbital type. And then we have a superscript, and it must be a superscript number that tells us how many total electrons are in that energy level, or in that, not energy level, in that orbital. Okay. So for example here, we would be looking at 5 electrons in the p orbital in the 4th energy level. Remember, we make like a list of these to describe where every electron is in a specific atom. Okay. We can also use orbital diagrams. So in our orbital diagram, the box, so this is the orbital diagram for lithium, the box represents an orbital. The arrows, each arrow represents an electron. one pointing up, one pointing down. If you have 2 electrons in your orbital, and never have more than 2 electrons in an orbital. The different directions represent the different spins. So here we would only have 1 electron. By convention, we write the up arrows first. It's important that you label the boxes in your in your orbital diagram. That way we know that you're representing the correct thing. So each s orbital would have 1 box. Each p orbital would have 3 boxes. D orbital would have 5 boxes, representing the 5 different possible orbital types within that type of orbital, I guess. Okay, so we have rules for filling these. Pauli exclusion principle is one of them. We talked about that a minute ago. But there's also Hund's rule, remember, which this is, I think in regular chem we talked about this is the empty bus seat rule. Basically what it says is that you have to fill the lowest energy level first, and that those electrons need to spread out over the energy level before they pair up. So there must be 1 electron in each orbital before pairing, and the electrons have the same spin as much as possible. So for example, if we look at, let's look at carbon here, right, we would fill this orbital first, this is the 1s, then we would fill the 2s, and then with our remaining electrons, before we paired them up, we would spread them out over the 2p. They wouldn't sit next to each other. They would want to move as far apart as possible, and that's to minimize the amount of repulsion that they feel. This is kind of like, remember we called it the empty bus seat rule, because if you got onto public transportation, you're probably not going to just go and sit next to the only other person on the bus. You're going to find an empty bus seat or an empty seat to sit in. You're only going to sit next to someone if you absolutely have to, and that's similar to what these electrons do. Remember when we write our electron configurations, we can condense them. And one thing to there's just a couple of things here to kind of remember. If you're in the same group on the periodic table, so here we're looking at the alkali metals, but any group on the periodic table, you're going to have the same number of electrons in your outermost shell. Those are your valence electrons. Remember, we have a maximum of 8 valence electrons. The filled inner shell of the electrons, those are the core electrons. And they include completely filled D or F sublevels. And we can write this condensed electron configuration. We call it like the shorthand version or the noble gas configuration. And the way that we do that is we look to the noble gas that comes before the element that we're trying to write our electron configuration for. So for example, neon comes before sodium on the periodic table. It finishes off the row before it. So we write neon in brackets, that represents the core electrons. And then we build our electron configuration there. And so sodium is in the 3rd energy level, and it has 1 electron in this s orbital. And so the 3s1, that represents where the valence electrons are. So sodium has 1 valence electron. And this can save us a lot of time because we don't have to write out all of those core electrons. I want to remind you, if you are writing the electron configuration for the noble gas, you can't just put, like if you were writing the electron configuration for neon, you can't just put neon in brackets. You need to go back to the noble gas before it and build from the previous noble gas. We fill our orbitals in increasing order of energy. This is just to remind you how we do this. So here's what your periodic table actually looks like. Usually we pull out the lanthanides and actinides and put them below, and then we squish the D block next to it. But the lanthanides and actinides actually fit in right here between the S and the D block. And so we would build across to write our electron configuration. So the blue here, these are, this is the S block. The pink is the P block. The orange color, these are our transition metals, or the D block. And then the tan is the lanthanides and actinides, which is the F block of the periodic table. So here we have it written in as 3D, 4D, 5d, 6d. Remember the D block, before you use it to write your electron configuration, you want to look at the row number and subtract 1 from it. And for the F block, you want to look at the row number and subtract 2 from it. We'll do some more practice with this in class, but this is just a quick kind of overview to remind you of what we do for these electron configurations. Now, I don't know that there's a place to specifically put this in your notes, but you definitely want to write this down. So in regular chemistry, when we did these electron configurations, we didn't really talk about these anomalies, but there are some elements in the D block of the periodic table that where their electron configuration doesn't really follow the normal pattern. And these are situations where you could end up with a filled D or a half-filled D. And that, for these elements, is more stable than having a full S. So we're going to look at chromium, which is right here on the periodic table. It's number 24. It's our first example of one of these anomalies. So the expected electron configuration for chromium would be, and this is, again, the noble gas configuration, so argon, and then we have 4s1, 3d5. Sorry, that is the actual electron configuration. If we were to just write it following our pattern, what we'd write is argon 4s2, 3d4. But this is less stable than to have a half-filled D shell and have 1 electron in your 4s. And so this right here actually ends up being our electron configuration. And the reason that this can happen is because the 4s and the 3d orbitals are really close to each other. And so the electrons kind of move in whatever way is most energetically favorable, and will produce the most stable situation for them, which has to do with either half filling or completely filling the D block. This occurs in the F orbitals as well, but we're going to mostly focus on the D orbitals. I definitely want you to write down these exceptions. You don't necessarily need to write down all of the electron configurations for them, but chromium and molybdenum are both half-full D exceptions, so they're going to fill up the D orbital to halfway instead of having a complete S. Okay, and then in terms of full D exceptions, meaning that it's more beneficial for these elements to have a complete D shell than to have a full S shell. We have copper, silver, and gold. Those are examples of elements that are exceptions to the standard electron configuration. So make sure you jot these down, maybe next to the periodic table at the bottom of your notes. When you see these elements, you're going to want to recognize them as being exceptions to your standard electron configuration. And again, that's because having a half full D or a full D imparts some stability to these atoms that they wouldn't see if they had filled up the S completely. Okay, and then I just wanted to show you this. You don't need to write this down anywhere. This is like what the orbital diagram would look like. So in chromium, you can see that the electrons would be all the way spread out here. And so that's probably more stable for it than having this right here totally full. And they've reversed the order of the 4s and the 3d, but we really want to write that in the other order. Similarly, for copper down here, you can see that we have a full D shell and just 1 electron out here in the 4s. And again, this happens because this 3D and the 4D, the 3D and the 4s level are really close in energy, so the electrons can kind of move between them as would make the most energetically favorable situation for the atom. Okay, so I think that's where we're going to leave off with our notes here. In class, I will give you some more instructions, I'll give you some more instructions about what we're going to do. Okay, thank you very much. Bye.